Um, Pleasant good evening, one and all. A very warm welcome to each and every one of you to this special online session commemorating World Quantum Day 2025. This event is proudly organized as part of VIT Quantum Mission, aiming to spread awareness and inspire curiosity about the exciting advancements in quantum world. Today, we are gathered here to explore the fascinating realm of quantum machine learning, a frontier that holds immense promise for the future of technology, science, and innovation. We are honored to have with us Mr. Rajiv Mistry, our esteemed resource person for this session, who will now take us through today's session on quantum machine learning. Moreover, he is here to enrich us with deep insights into the quantum world and guide us through the exciting possibilities that arise when quantum computing meets with machine learning. Let's join together in warmly welcoming here. We now request Dr. Geeta Ma'am, Dean of Research, to do the honors of facilitating our esteemed guest and also give the speech on significance of World Quantum Day. Ma'am, over to you, ma'am. Thank you.
Ma'am, am I audible?
Yes, ma'am. Audible, ma'am.
So good evening to everyone. It gives me great pleasure to welcome you all to this special webinar on quantum machine learning organized as part of our World Quantum Day celebration. So that's been an interesting fact. Why actually 14th of April, 14/4 is marked as World Quantum Day. The reason behind that is in reference to Planck's constant 4.14 into 10 power minus EV. So that 414 is taken and that has been adopted as World Quantum Day, especially international celebration of quantum science and technology to raise public awareness and highlight quantum research's transformative potential. Though it is in the beginning stage or it's not been well reached in all aspects, but this quantum science, quantum computing is doing fantastically good. It's been one of the most intriguing and transformative fields of modern science. When combined with power of machine learning, you can do a lot of stuff because machine learning is more related with computing and machine learning more related with computer science. So from faster computations to solving complex optimization problems, which were once thought impossible, especially this quantum cryptography, where the key generations and then breaking of that cryptanalysis, everything is done in an impossibly faster time. Today, we are truly honored to have with us Mr. Rajiv Mistry, a well-known expert in the field of quantum computing and machine learning. So we are very privileged and honored because he will be sharing his insights on cutting-edge intersection of technologies. His vast experience and deep understanding of both theoretical and applied aspects of quantum machine learning are sure to enrich our perspectives and spark meaningful discussions. On behalf of School of Computer Science and Engineering, VIT Chennai campus, we extend a very warm welcome to Mr. Rajiv Mistry and to all the faculty members, the research scholars, the students, and all the participants who have joined us for this intellectually engaging session. As far as quantum is concerned, like you have got in quantum computing, where all the big technological business people are investing, like IBM, Google, Microsoft, Amazon, and startups like IonQ and Rigetti. They are making quantum computers more powerful and accessible. Cloud-based quantum access. Even Sridevi ma'am is having a project funded by MIT, where the IBM quantum instances are given to you. Amazon Bracket allow the developers and researchers to run quantum algorithms remotely. So you can try, you don't need any investment on this one. This web services is helping you a lot. Cloud-based web services. And then quantum advantage, quantum supremacy, quantum machine learning. I mean, like it's increasing the true power. And then you can even try with software like this, Qiskit, PennyLane, and a lot of other stuff which are completely open source and free for the students to begin with and try. It's like quantum, it's picking up like anything, maybe in the near future or maybe in a decade, we can see the quantum laboratories in almost all the institutes. And we are very much eager and curious to listen to the speaker, like what is happening in this way, and what is say with respect to machine learning, what are the perceptions and what is occurring in the field. So it's been like very happy to have you with us, sir, and we welcome you for that. Over to the speaker.
Thank you very much. The honor and privilege is mine entirely. So I want to, first of all, congratulate and pay my respect to the faculty at VIT Chennai, the scholars and researchers who have gathered today to celebrate World Quantum Day, along with the most important audience, the students. So, I would like to share my screen and walk through some concepts around quantum machine learning. Please let me know when you're able to see my screen share, and I'm going to turn on my full screen share.
Yes, sir. We could see your screen.
Okay, very good. Let me see if I can hide this panel. Hide floating controls. There we go. Okay, so today's presentation, and if I look sideways, is because my webcam is on my main screen on my Mac, and I'm looking at the second display. So pardon that. But today's presentation is on quantum machine learning and state-of-the-art in applications that are using the amalgamation or hybridization of classical machine learning, which is now a fairly mature field, and the up-and-coming quantum machine learning field. So I'll be walking through some really intriguing aspects by covering the following agenda. I'll start with an introduction and then cover very quickly quantum machine learning basics, where we will talk about an overview for machine learning. What is the typical workflow in classical machine learning? What are neural networks? And then we'll touch upon quantum computing basics, quantum machine learning, what are some algorithms and techniques? And then we'll talk about applications where the science and theory meets real-world applications. Lastly, I'll talk about challenges, and then in the references section, I'll talk about what are the sources of the information that I'm sharing today, followed by a brief question and answer session. So I think we have almost 2 hours for this presentation, and let's dive in. So as an introduction, how many of you know about a thing called a qubit, and how many of you know about Bloch sphere? Just by show of hands, or speak up by unmuting. Okay, I'll continue. So, classical computing has been, oh, Chandra knows. Okay, good. Thank you for sharing that. In classical computing, we typically use 2 states, bits, 0 and 1, and the entire classical computing foundation is based on creating binary data sets using 0s and 1s combined into words, which are then processed on CPUs. And we have this thriving ecosystem of applications that have grown in the last half century to give us our world as it is today, right? When we look at quantum computing, it's a much bigger set of states that we are able to address in terms of computation. Let me explain that by looking at an imaginary sphere. Imagine a sphere with a unit radius of 1. And on the upper left, this sphere is shown with a cross-sectional view. On the north apex, or the north pole of the sphere, is a 0. And on the south pole is a 1, okay? The unit vector that goes from the center of the sphere to the surface is what we are looking at as a Bloch vector. Now, the Bloch vector is essentially a representation of the quantum state represented by a Hamiltonian equation, okay? As you know, there are three types of mathematics: Euclidean, and Hamiltonian. Quantum computing has been entirely focused on Hilbert spaces and Hamiltonian mathematics, using the concept of the unitary sphere or Bloch sphere, in which the classical bits are just 2 points on the entire surface of the sphere. The number of states available on the surface of the sphere are infinite. This is what is addressable through quantum computing, not just 2 states as in classical, okay? And typically, we do this by measuring the estimated phase rotation and the amplitude of the vector, okay? And on the lower left in the diagram, there's an equation, ket psi equals alpha ket 0 plus beta ket 1. This is basically looking at probability amplitudes when squared as alpha and beta, and ket 0 and ket 1 are essentially the operators that we are using to come up with the state definition, which is psi, okay? So, and I've covered quite a bit here, so I won't belabor this detail, but, you know, classical machine learning essentially uses classical computation and is bounded by the binary state that I mentioned, zeros and ones. And it uses this to tremendous advantage by, you know, using forward and back propagation in neural networks, or, you know, applying binary states for various operations where you can come up with machine learning calculations. It remains bounded in binary error propagation and correction techniques. In other words, whenever you see an error accumulating in a feed-forward network, or, you know, when you're applying back propagation to take care of those errors that are accumulating, those are correction techniques, you're still bound by binary. It's not able to go past the zeros and ones. One advantage with classical machine learning is that you can actually reprogram the hardware using FPGA GPUs. FPGA is field programmable gated array, which is essentially a reprogrammable hardware device that can have a model overlaid on it. And the model is basically a machine learning model. And you can train it iteratively. And if you need to make corrections, you can reprogram the FPGA very easily. That's the advantage that GPUs offer us today, okay? So it's becoming computationally very expensive, because obviously the more complex your model is, the more neurons you have, the more layers you have, you will have explosion in computational need. And so, you know, it becomes prohibitively expensive, both from the perspective of investment in hardware, as we are seeing today, as well as in terms of whether some very large problems are even addressable using classical machine learning, okay? It's also highly sensitive to input parameter changes. In other words, if the model has been trained on a certain set of input parameters, if those parameters change drastically, then you have to retrain the model. And so, you know, using this approach to reach model convergence before it can be applicable for a given real-world application is something that requires retraining. And so, you know, the expense in training once iteratively is multiplied by the number of times you have to do this based on input parameter changes as your application evolves and your needs evolve in terms of providing inputs that are more and more detailed and sophisticated. Now, contrast this to quantum machine learning. It uses quantum circuits to address all input states simultaneously via qubits. And qubits, as I just explained earlier, have an infinite number of addressable states. So you can have 2 qubits that you can entangle in a quantum circuit using quantum operators, and gates can be used to conduct various phase estimations or amplitude estimations, and even control the state itself to the point where you are now using state evolution directly through Hamiltonian manipulations in a quantum circuit, okay? If applied to the right size of a problem, it can be very fast, accurate, and efficient in assisting classical model training and convergence of such ML models. Now, on the upper right, I've got a diagram that's showing two exponential curves and a linear curve, okay? And on the y-axis is time to solve, on the x-axis is problem size. Basically, this is showing that if you have, a small problem and you have a solution, an ML solution that's going exponential very quickly. Oh, I'm seeing some scratches appearing on my presentation. I don't know what's going on. Does someone have their pen on? Could you
Dear
please
students,
Yeah, I think someone's done something.
And you can, you can remove them, or you can control, like, kind of.
sure, ma'am.
Well, I don't know how to take out the annotations. That's the problem. So Laureen S., that's the person who was doing that. Please undo what you were doing. Or I can just reshare. Hang on. There we go. Let me just reshare my screen and it should take care of the issue. Okay. All right. So going back to what I was saying, when you have a small problem and you have a classical solution that goes exponential in its time to solve, the crossover between the linear solution and the exponential solution is closer to the problem size. And so in the space between the linear and the exponential curve, you have an addressable solution. If you have a large problem, then you need a larger classical ML model that is going to go exponential with much higher resources. And so the addressable problem space is under the linear curve up to the crossover and the exponential curve. So the point being...
Sir, excuse me, sir. The presentation is not visible. The presentation is not visible, sir.
Okay, sharing is not turned on. Someone has taken over the share. Could you please make me host again? Co-host?
Yes, sir, please. Yes, 1 minute. Yes, sir. I have given the co-host option, I think.
Good. Got it. It's working. All right. Sorry about the slight technical issue here. But what I was explaining was for small problem sizes, is the area addressable beneath the linear and the first exponential curve. For larger problem sizes, the ML model size increases, and so the addressable space becomes larger, right? So in terms of quantum machine learning, we have some limitations, and I'll talk about those later on. But keep these concepts in mind as we dive further in, okay? So now addressing quantum machine learning basics, there are, and this is a Venn diagram that I've shown here, AI encompasses ML, which encompasses deep learning, okay? That's the gist of the story here in terms of classical machine learning. AI leverages math and statistical theories and looks at processes to create intelligent programs or machines that can proactively solve problems on their own, okay? And it's often categorized as weak AI, strong AI, super intelligent, or superhuman AI, as you call it. There's also, the concept of AI becoming self-aware, as you've seen in science fiction movies, but that could very well occur in a near future. Machine learning is a subset of AI, and it uses mathematical and statistical insights to endow a computational system with the ability to automatically learn and improve its efficiency. So, it requires training, and they can be achieved using various types of algorithms, which we'll touch upon briefly in the next few slides. Deep learning uses neural networks. So unlike ML, which can use different algorithms, deep learning typically uses neural networks, and I'm going to dive into some details in the upcoming slides as well. There's a concept called perceptron, which then leads to activation, and there are different types of activations that you can use to control a neuron and a set of neurons to create a neural network. And then quantum machine learning, that is something that uses quantum circuits, and we can use quantum neural networks to address much higher or multiple dimensions because you have infinite states addressable. So you can increase the dimensionality of the problem that you're addressing using quantum neural networks. And lately, quantum convolutional neural networks have come to the forefront in terms of lowering the computational burden on classical convolutional neural networks. Okay, so there's some classical data encodement that is required to quantum states before you can leverage superposition that then drives quantum circuits where you have gated circuits, or you have annealing circuits, and then you can come up with outputs from those that you can post-process classically. In terms of machine learning, there are a few things that you have to keep in mind. Different types of machine learning models are shown on the left, and there are two different considerations: bias and variance. And without getting into too much detail about what these mean, which you can look up on your own, essentially, increasing bias decreases variance, and decreasing bias increases variance. This is the mutual trade-off that happens, okay, in classical machine learning models. So the holy grail here is to find the perfect spot for optimized performance as allowed by the model complexity. So, you want to have accuracy and model complexity where, if you have the right amount of fit between generalization and training, this spot here, the perfect spot, then you would be able to have the right solution. And overfitting or underfitting of data is a big problem in ML. You have to be very careful not to do either. And that's where the science is led by art in terms of experimentation and empirical learnings. So overestimating a predictive outcome based on insufficient amount of data is called overfitting. And obviously, if you use insufficient amount of input data, your predictive outcome might look good, but it'll be wrong. It'll mislead you in the conclusion for the experiment you're handling. And so your application could malperform in real-world circumstances. Underfitting happens when a relatively rigid model is used in play, which is too simplistic to capture all the trends in the input data. So, you have a simple model and you're using a complex input data set that is not capable of being addressed by the model. And all of a sudden you have results that look good, but they're false. So both have to be balanced, okay? So bias and variance trade-off, and also hitting the sweet spot between overfitting and underfitting of data. That's the name of the game in machine learning. So in terms of the machine learning workflow, there are three things that you have to keep in mind. First is the cycle itself. You have to prepare the data through data collection, cleansing, processing, build the model using data exploration, feature extraction, which algorithm to select and apply, and then build the model. And then you do the model evaluation where you estimate the error and you do the accuracy calculations, based on which you then iteratively optimize the model. The training data and the adjustment of the model parameters is critical in the optimization. And this loop continues until you have arrived at an acceptable error and an acceptable accuracy. And then you deploy the model for the test data set, okay? And that's when your model is now deemed to be in production and you can visualize the output from it for real-world applications. On the right is the method of training the model, where the data is split into 80% data for training, 20% for test. When you train the model on 80% and arrive at the required efficiency or acceptable efficiency and accuracy, and there are other 7 or 8 other parameters they're also important in terms of evaluation of the model. You then apply the test data set for real world application. And you can do this in terms of validation exercises where you split the data set into 6 different runs, and the splits are done in such a way that you test repeatedly across different splits of the data set and keep on consistently improving accuracy until you arrive at the acceptable accuracy levels. So this is the workflow that goes on in most ML models in the classical world. Let's talk about neural networks now. On the left of the slide here, we have a simple perceptron. And a perceptron is modeled after a neuron, a biological neuron in the brain or in the nervous system. It has inputs. There are some weights. These weights are then used to drive an input function, which, in this case, we are looking at the decision on whether to attend a sports event. And you're looking at inputs as the weather. Is the star player going to be playing? Is public transport to the venue of the sport event available? And can your friends accompany you? And then you put weights on it. And based on the input function, you calculate the activation function, which is the step function. The activation function, when it hits a criterion, let's say the weighted sum has to exceed 60 in order to have a go decision, then if you arrive at activation at 60 or higher, you say, okay, let's go to see the cricket match. If you arrive at a lower number, you say, don't go. Okay. So this perceptron is something that is used as a unit in a neural network. And you can have multiple neurons or multiple perceptrons, and you can have layers in which you have an explicit or visible layer, and then there are hidden layers that drive a feed-forward functionality until you converge on the calculation for the input function, and you can drive it using different types of activation functions. Okay. First is linear activation. The second is something called ReLU. The third is TANH. And the fourth is sigmoid. So these are different types of activations that you can use to arrive at your decision outputs. Okay. And I'm not going to belabor this, but you can look this up. It's well documented. You can go out to, certain applications that are available that I'm mentioning in slides later on. Okay. So I've covered a lot here, but you can go to playground.tensorflow.org and you can play with actual neural networks to see what they do. Okay. You can increase the number of perceptrons, the number of layers, hidden layers, tweak the parameters for the inputs, the weights, and see what results you get. It's a fun exercise. So that's an assignment for you after this session is over. Now let's talk about quantum computing basis or basics. The quantum computing application requires an environment in which you can program for quantum job processing. And for that, you need a provider, a backend, and the job itself. So there are various frameworks that have come about. One is Qiskit, another is QSharp. Qiskit is by IBM Quantum. QSharp is by Microsoft. And then, you've got PennyLane by Xanadu and, StrangeWorks. There's so many different frameworks that have come about. But essentially, the workflow is something like this. On the upper right, I've shown a diagram that says you have a quantum circuit. You have a transpiler that compiles the circuit for the backend. You select the backend and submit the quantum object, which is typically a matrix formatted input file from the input parameters, which may be analog or digitized. And this quantum object is then submitted to the quantum processing unit or the simulator on the back end. Okay. The provider is what allows you to decide which backend is the job being submitted to. It can be either a simulator or a real device or a quantum processing unit. And then the job is processed using a quantum circuit that has various operators and gates. And then these jobs come up with results that are then post-processed on a classical computation platform. So this is basically the Qiskit workflow, but it applies to any quantum framework. And then, there are various types of quantum processing units that we have. There are two categories chiefly, gate-based and non-gate-based. This all started with non-gate-based computation annealing by D-Wave, which is, probably 15, 20 years old at this point. And now we have a new entrant from QEra, which is also offering annealing, and they're starting to do something really interesting, which is using annealing approaches. They're creating gate-based circuits. Very unique concept. And then there's gate-based QPUs. There are many types of gate-based QPUs. Superconducting, they're transmon qubits or artificial qubits. IBM and Rigetti use these. These typically require near absolute zero temperature, which is why you have these big refrigeration units in which the QPU is housed and kept isolated from noise and kept extremely cold. It makes it expensive to run superconducting transmon qubits. It's also very subject to noise from the environment. Dark noise from the cosmic background radiation can upset superconducting QPUs very easily unless you go very deep within the Earth. Trapped ion, which is ionized atoms as natural qubits. IonQ is the foremost in that. And they use lasers to control trapped ion movements by shuttling these ions and lining them up, suspending them in an electromagnetic field, and then also use adiabatic cooling for achieving near absolute zero temperatures using lasers instead of using other means. There's also microwave-based cooling that is being applied to trapped ions in the UK. It's in the research stage, though. It's not commercial like IonQ. We have photonic qubits. Xanadu is the foremost. It's a Canadian firm. It's been working on photonic quantum circuits where they've got an entire paradigm of gated quantum computation using nothing but photons in optical channels. One of the big issues there is that it tends to leak from the fiber optics. And so you have decoherence, and they're contending with that with various tricks. Nitrogen vacancy diamond, which is atomic qubits. Great Lakes Computing in Michigan is working on that. Basically, there's a carbon atom within a nitrogen set of atoms in a diamond, and it creates a vacancy in which you can now manipulate qubits. Neutral atom, which is natural atom qubits instead of ionized atoms. That's something that's going on with atom computing in Colorado and Pascual, which is a French firm. And then there's topological qubits, which is the effort that is singularly by Microsoft. They're using something called Majorana qubits, and they've come up with a new QPU that they're claiming is able to detect Majorana particles, which can lead to entanglement, but they've not yet proven the existence of a Majorana qubit yet. So I've spoken a lot here, but these quantum processing units can form the lowest layer in the full stack that makes up a quantum computing platform. Okay, so the physical apparatus is what different QPUs can be residing in, and these include quantum dots, lasers, MEMS mirrors to control lasers that cool them, shuttle them, etc. And then you send the data from these up for virtualization, and it couples with open loop error cancellation. And we apply concepts like dynamic decoupling to be able to then further use frameworks for quantum error correction in the layer 3. And you can then apply various techniques depending on the kind of QPU you're dealing with for error correction. And then you can do logical calculations using gated quantum circuits. And based on the logical qubits, logical gates, and logical measurements, you can now drive quantum algorithms and have an interface for a quantum application for a classical user. This is how quantum computing works, okay? Let's talk about quantum machine learning. And I know I'm going really fast. We have about 50 more minutes, so let's see if I can speed things up. QML algorithms are basically using gate-based quantum circuits, and they use something called quantum parallelism, okay? This is based on the addressability of infinite number of states in a quantum algorithm via quantum circuits. And you can then manage qubits, multiple qubits that are entangled with each other through quantum circuits that apply something called a Hadamard gate to entangle any two qubits and apply various types of gated operations that I will not dive into, but you can essentially construct an entire algorithm using qubits that are represented as wires. So let me touch upon the diagram here. The line that you see that runs horizontal is called a wire, and this is a qubit. So in this case, we are depicting 8 different qubits as 8 separate wires on which you have different types of quantum gates that are placed. And then based on the entanglement between the qubits, you can then have different operations applied. What is shown here is a quantum Fourier transform circuit. And there are different types of algorithms that you can check out by going to the site for Quark, which is a web-based application that allows you to examine different types of quantum algorithms and play with them using different gates that you place on different numbers of qubits and then apply operations. And it shows you how it's actually doing a simulated calculation. So this whole approach has been divided into various sections. And it started with a researcher named Deutsch. Deutsch came up with the idea of quantum computation and the associated algorithms by working on something called universal quantum computation. And this was very recent, 1985. So, he based his work based on Richard Feynman's ideas, where he talked about quantum mechanics, and he said, we need a quantum computer, but if you think you understand quantum mechanics, you're wrong. No one understands quantum mechanics, okay? But you can study it and do some meaningful things trying to understand it. So he developed quantum algorithms for computing and communication. There's also hardware for computing and communication that has to be developed. We seek solutions for robust fault tolerance because there are errors that happen in different QPUs based on the type of technology. It has some different behaviors in terms of being error prone. You can develop quantum algorithms for machine learning. We are working on improving scalability and then seeking proofs of universality. So this is what has driven the evolution of QML algorithms, okay? And one of the big things that happened was Peter Shor, who now teaches at MIT, came up with the proposition that phase estimation can be done by using Fourier transforms, but applied to a quantum circuit, so a quantum Fourier transform. And he predicted that you could factorize numbers into prime numbers and essentially break all encryption, provided you have a capacious enough quantum computing platform. It hasn't happened yet because of the issue of errors in QPUs, but it could very well happen sometime in the near future that QFTs are used to crack classical cryptography. Let's talk about algorithms and techniques. So QML has many different algorithms. Some of the foremost ones, I've picked 3 here, but there are many, and you can dive into some details based on the reference material that's in the last slide. We'll get there in a few minutes. But essentially, you have a manner of working with classical and quantum hybridized architectures that is shown in this circular pattern here. You take input data that is classical for a known problem set, and you pre-process it so that you do the state preparation and do the transformations for a quantum circuit to calculate, and then you measure the output of the quantum circuit. When the measurement is done, the entanglement in the quantum circuit disappears. And this is called the collapse of the probabilistic wave function, for those of you who know quantum mechanics well. But that measurement essentially results in a classical data output, which you can then post-process to review the results from the quantum circuit calculation. So this cycle is repeated until you reach meaningful results that are highly accurate and are also more efficient than classical means. So, and I've explained what goes on here, but in terms of state preparation and circuit execution, you do a unitary transformation, and that unitary transformation is then submitted to the quantum circuit to then perform a measurement, and you post-process the results. There are some different types of encoding that you do in pre-processing, right? There are decisions you make about what type of encoding will you use: basis, amplitude, tensor product, and Hamiltonian encoding to take the classical input data set and encode it. The psi function here is encodement into a quantum subsystem, which is based on operator math, which is why we've shown a Ket signature here. The quantum subsystem is then able to execute once the data is encoded in the appropriate format. Three different algorithms that are meaningful here: quantum support vector machines, quantum convolutional neural networks, and quantum annealing. These have, different applications. SVM is optimized using quantum states for faster classification, which is, Bayesian classification, if you're familiar with that. QCNNs enhance learning speed by leveraging quantum gates, and these are used for image processing quite heavily these days. And then quantum annealing, which solves optimization problems using quantum fluctuations. There are other algorithms that address optimization, such as QAOA, VQE, etc. I won't dive into the details there in the interest of time, but feel free to look at that detail by going online into the Qiskit book. It explains all these concepts really well. Let's talk about applications now. What I've shown here is a generalized architecture for waveform analysis using quantum convolutional neural networks that can augment classical convolutional neural networks using pre-processed wavelets from input signals. Okay, so on the left, you have an input waveform that is encoded, and you apply discrete wavelets to transform to create the pre-processed scalograms that are then used by a convolutional phase to create the encoding layer, which essentially gives you your input matrix for the quantum circuit layer, where all your gates do the operations on the input that is encoded in the right format, which is typically a matrix, to process it. And then the decoding layer is where the measurements happen. And these measurements then create a quantum feature map that can be used in a classical convolutional neural network to do training and testing using in this case, is a 70-30 split between training data set of sample outputs of quantum feature maps versus testing samples. But you can drive it in a loop through a multi-layered perceptron QNN or classical CNN, and you come up with the outputs that then give you your decisions. So this is a generalized approach that is applicable to many problems. You have various metrics that can be used to evaluate the performance of this kind of a hybrid architecture. Some of these metrics are shown on the right: Jacquard index, accuracy, F1 score, recall, Matthews correlation coefficient, and precision. And some of the work that is being done today by Dr. Sridevi and her students, and I'm collaborating in some of the validation work, is focusing on quantum Fourier transforms and QCNN, CNN-based ECG anomaly detection in cardiac waveforms, or QCNN and CNN-based EEG anomaly detection for brainwaves for detecting epileptic fits. And then I've done some prior work in quantum Fourier transforms to detect top 5 frequencies in given audio waveforms to be able to have healthcare applications or audio processing applications in the music recording industry or in the live concert industry. Okay, so I'd like to give the floor to Dr. Sridevi to talk about some of the work that is underway on EEG anomaly detection. Dr. Sridevi, please go ahead.
Yes, sir. Thank you. Thank you for the opportunity given. So let me just share the screen.
Okay. Sorry, I'm trying to unshare and I've lost my, hang on, there we go. Okay, you can go ahead and share. We see it.
Yes, I think it's visible. So good evening, one and all. So first of all, I would like to thank Mr. Raju Mistry for collaborating with us for this particular research work. So this is some prayer work. So I just wanted to portray it over here. So based on this prayer work, so we got an opportunity to collaborate with each other. So the details of the prayer work is all about convolutional neural network to recognize arrhythmia from 2D scaleogram features of ECG signals. So this was presented and got published in IEEE Explorer. So it was a conference presented in IIIT Kottayam. So the overall architectural facts about this research work was that, so the data set taken for this research work was obtained from MIT BIH. So it's a collection of arrhythmia data set where we have 5 different classes. So the thing is like, though the ECG signal is itself is an one-dimensional signal, so we thought how to convert the signal processing into an image processing task. So we thought we searched for some kind of literature where we found a scaleogram processing available for ECG. So inspired on that, the MIT BIH arrhythmia one-dimensional ECG waveforms are converted into 2D scalograms by applying discrete wavelet transform. So this was the first step of pre-processing done, where all the 5 different classes ECG signals are converted into 2D scalograms. So once images were available, those images are undergone convolutional phase, where we have this 3 sets of layers where encoding, unitary transformation and decoding is done. So the first layer in this convolutional part is like all the classical bits available in the scaleogram images are converted into quantum qubits undergoing amplitude rotation gates. So this is the part of encoding. So once this encoding is done, all the classical bits are converted into qubits. So now the second layer with multiple depth, where circuit depth is framed with unitary circuits, where we can make use of different configurations of quantum gates. So the unitary circuit used over here comprises of rotation gate and Hadamard gate. The purpose of having Hadamard gate is to enable a superposition to have qubit to be represented in multiple bits at the same time. And entanglement is also enforced by means of having C0 gates. And following the unitary circuit, so once the processing is done in the qubit, then finally the measurements are done. The measurements are done with the help of poly-Z gate. The poly-Z gate are the one which measures the qubits extremely north and extremely south. So as Raju Mistry was mentioning in the first slide, the block within the visualization of the block sphere representation, the extreme north and south represents qubit 0 and qubit 1. So the superpositioned representation of all the qubits are converted back to 0 and 1. So while doing the measurement, all the superpositioned qubits will be measured exactly in the different probability counts with respect to zeros and ones. So these three are the layer which undergoes convolution. So the thing is like, though the images are of different sizes, say for example the scaleogram image is 100 cross 100, so like the raster scanning, the entire images considered in the kernel space of 2,2 is processed with the help of this convolutional layer, and it is being converted into quantum feature maps with 4 channels. So the reason why we have 4 channels over here is like the size of the quantum circuit used over here had 4 qubits. So each wire is responsible to develop a quantum feature map as a output channel. So once this processing is done with respect to quantum learning, the next phase is involved with deploying ordinary classical convolutional neural network. Since the output of this convolutional layer is just a shortened version of the 2D quantum representations of the scaleogram images, it can be converted into one-dimensional vector, and then it can be processed with one-dimensional CNN, normal pooling layer. So as many number of convolution layer, whichever we want as per the problem statement is concerned, and maybe stacked back to back, and finally a dense layer followed by the classification layer. So in this case, the problem statement is to classify whether the test query ECG signal belongs to either of the arrhythmia class or healthy class. So the classification layer has 5 nodes at last. So based on this, we were able to come up with a hybrid quantum and classical neural network, which were able to give exceptionally very good results compared. So this is the output. See, this is the original 2D scaleogram images shown in the first row, followed by 4 different rows. All the 4 rows are the output quantum feature maps or activation maps. So in general classical terminology, we used to call an output of a classical convolutional layer should be called as activation maps, right? So very similarly, the output maps of the convolution layer over here is obtained, calling it as convolutional quantum feature map. So these 4 layers corresponds to quantum feature map obtained from each channel. So we got 4 channels, and this is the output for 4 different images of scaleogram, 2D scaleogram images. So this is the research outcome we were able to do. Very similar to classical hyperparameter tuning. Over here in this quantum circuit, we may be able to do quantum hyperparameter tuning by changing the number of layers, by changing the number of shots. So over here, since we tried changing the number of shots to 100, 500 and 1000, irrespective of any number of shots, the results were given same. So in this analysis, we kept the number of shots as 1000, and by changing the quantum circuit depth or number of layers from 1 up to 4, we conducted the results back to back, and after the analysis, we were able to obtain for number of layers is equal to 2, means quantum circuit depth, how many number of time the unitary gate was repeated. So based on the analysis, we were able to find with 2 number of layers for this hybrid convolutional neural network, the results were better than the 2D CNN model. And these are the model accuracy for training and validation sets, and the receiver operating curves for arrhythmia detection. So thank you. Thank you for the opportunity given. So
You're welcome. I'm taking the share back,
yes.
and we can continue on. Okay. So having addressed the different applications that we can use hybrid architectures to augment CNN capabilities by making them faster, more performant, highly convergent, more efficient, more accurate, etc., using QML, what are the challenges that we face today? So I've thought long and hard about what are the top 3 challenges, and I've noted those here. And there could be many more, but in my perspective, given the state of the art today, we have these 3 big challenges that we need to solve. The first is the results for the same quantum circuit are dissimilar when you apply a simulation versus a real device QPU execution for the circuit. Simulators are error-free, but use classical CPUs, and they can only be used to simulate small quantum circuits. You can't have a very large number of qubits in a simulator because it rapidly runs out of steam in terms of the available CPU compute power. So they cannot scale in the real world applicability, but they can be used for validation of quantum circuits in terms of whether it's functional for the purpose that we are designing the application for. QPUs, on the other hand, are noisy and error prone. Okay. And that's why we are in some say the NISQ era, noisy intermediate scalable quantum computing, because we can't get rid of the noise in QPUs because of various reasons. And dark noise is one of the biggest ones. It creates havoc in 2 or more entangled qubits. And so decoherence is a big problem, and you start having erroneous results. And so QPUs also cannot scale to real-world applications. So how do we get to a point where we have real-world applications that are able to absorb real-world scales of data? For example, the cardiac anomaly problem that was just discussed by Dr. Sridevi. If we want a real-world application to detect patient cardiac anomalies, we would need a highly scalable hybrid architecture on a platform that is cloud and quantum enabled. And it should be able to absorb millions of ECGs inbound and process them instantaneously. That's not possible today. There's also the issue of the hybrid cloud-based high-performance compute clusters that host the pre-process data set in data lakes, data pipelines that do the encoding, et cetera, and coupling that to quantum providers that then submit the job to quantum circuits running on quantum hardware. That connection is something where what's happening is classical cloud platforms don't have uniform connectivity to all known types of QPUs. For example, Azure does not offer the same quantum providers as AWS, and IBM remains exclusive to its own IBM QPUs, right? Companies like IonQ, Rigetti, Pasquale, QEra, all these are clamoring to get on board with Azure or AWS so that they can be addressed via providers that connect to their hardware platforms. And they're also starting to offer their own private cloud where you can directly connect and do native gate operations on their specific tuned quantum hardware, okay? But it's not uniform. So there is a need for an evolution of standards where, in classical networking, you have standardized connectivity, which has resulted in the internet being so available worldwide. We don't have that in hybrid architectures with classical cloud and quantum providers being connected to today. It's not uniform. And it's chiefly because we lack standards. Okay, so there are efforts underway to develop standards, but it's nascent. It's in its infancy right now. The next few years, as QPUs become more stable, more scalable, less error prone, less noisy, we will start seeing the evolution of standards naturally. Okay. And the third issue here is quantum safe encryption and networking. When you're looking at QPUs where you want to do multi-QPU based large scalable circuit. Sorry? Someone said something?
Yes.
Okay.
Awesome. Okay, sir, please proceed, sir.
Okay. So, quantum safe encryption and networking is something that is a bit of a problem right now. You don't have quantum safe networking available as a quantum internet today. And the reason is you require carrier grade wavelength and frequency to match the optical transmission frequencies that classical optical networks use for high bandwidth connectivity. In order to have quantum safe encryption, we have limited durations and limited distances where these experiments are being conducted in various labs around the world. There's one right here in Chicago where I live. Chicago Quantum Exchange is building a quantum corridor in which they are doing work with University of Chicago, Purdue University, and Toshiba to build quantum networks to prove that we can actually go transmit quantum entanglement across carrier frequencies and wavelengths on optical fiber networks that are standardized. Okay, but it's still nascent. We don't have a quantum internet like we have the classical internet worldwide. It could happen soon, or it may never happen. We don't know. The work is going on, but these are three major problems that we have as challenges that if students, this is especially for you, you guys have a bright future ahead. If you focus your energies and efforts on resolving these challenges, you can make quantum computing worldwide. Okay? Take it as a challenge upon yourselves to work on these problems and solve these problems so that we can have quantum computing vastly available for inaddressable problems and solve issues that humanity faces. Okay? Going on, and I think this is probably the last slide in my presentation. These are the references, and we'll be sharing the PDF of this presentation with the audience so that you can click on these links and go out to the references to study further. I highly recommend you go click on each of these links and spend as much time as possible that you can devote to studying and understanding and practically exercising hands-on experiments using the material presented here. I think understanding theory is good, doing research is good, but you have to have a practicable applicability to real-world problems. All the links I've shown here drive toward practical applications using quantum capabilities. Okay, the first one is Quantum Programming in Depth. It's a recent book that has been published. It's actually in pre-publication. You can order it or pre-order it via Amazon. Maria Mikhailova, who until recently was with Microsoft Azure Quantum, she's gone to PsiQuantum, which is building highly scalable multi-QPU silicon wafer chips for QPUs. Then the second one, where most of my graphics came from, is Quantum Machine Learning and Applied Approach. It's an excellent, excellent book for practical QML applications. It's written by Santanu Ganguly. I believe he was at Cisco and has recently moved over to another company. I have to check where he has gone, but it's a really good book. And then the remaining links are all links that are reference materials for you to go study how to do quantum programming. Okay. GitHub has a quantum information kit, Qiskit, that you can study, which is the IBM methodology and framework. Really good way to go about learning all the algorithms that are mentioned in this presentation and more. You can do hands-on experiments by creating a free account on IBM Quantum and doing limited qubit exercises that are available as Jupyter Notebooks or code in this book. Algacert.com has Quark, where you can do what you see is what you get, kind of graphical quantum circuit programming. Just a fun place to go experiment and understand different algorithms from a visual perspective of how to do quantum circuits and what impact gates have when you tweak various quantum circuits and inputs and different encoding techniques. Azure Quantum, you can learn a lot about how to build some of the workflows that I talked about, but in a hybrid context where you have an Azure classical context with Azure machine learning, and then you have a quantum context with Azure Quantum Workspace. PivotPort actually has this in place, which is how we've done our research and development on quantum Fourier transforms for cardiac anomaly detection. And now we are starting to look into anomaly identification using some of the methods that Dr. Sridevi described here, wavelet transforms, QCNNs, and CNNs. And then you can learn about QML by going to the next two links, instruiq.com, machine learning or QML, and then ingenie.io, which is focused on learning for life sciences to apply QML to life sciences problems, such as drug discovery. And then lastly, if you're interested in getting a classical AI certification in healthcare, MIT X-Pro offers an online program. I recently completed that last year. It's a 2-month program, very intense, very hands-on. I highly recommend it if you want to get certified in it. So that's all I have. And what I would like to do is now open up for questions and answers. And hopefully I won't be able to answer all your questions, but I'll take away some of those, and Dr. Sridevi and I will collaborate to answer those questions that I can't answer right off the cuff. So floor is open for Q&A. Please use the chat function or just use your microphone to speak.
Sir, good evening. So in the chat already there was a question. What is gate-based and non-gate-based QPU?
Very good question. So if you look at gate-based calculations in QPUs, it is very similar to transistor-based gate calculations that are done in classical computation, except you're using quantum gates. Okay, there are many types of quantum gates. I won't get into the details of those, but the most elementary one that you require to start any quantum circuit calculation is the Hadamard gate, because it entangles two qubits. And the Hadamard gate essentially creates an entanglement using an operation that is then acted upon further by different types of gates to continue down the wires in a quantum circuit and come up with a measurable output. In non-gate-based quantum processing units, there's something called quantum tunneling that is applicable. And the idea is, if you imagine a three-dimensional surface where there are dents in the surface, imagine a net where you put a ball in the net and it creates a cavity in the planar net by just the weight of the ball pulling the net downward. Now the mesh of the net has distended, and if you apply the concept of gravity and you put a ball at the edge of the net with another ball in the dent, the ball at the edge of the net is going to spin inward and fall into the dent. Okay, so to get that second ball that fell into the net out takes work. The energy that it takes to get that ball out from the dent back onto the planar surface of the net toward the edge is what is required to drive the work in getting the ball out. In the quantum scale, the phenomenon of quantum tunneling can actually penetrate the dent in the net and just go straight across and emerge on the other side. It's called quantum tunneling. Without getting into too much detail, annealing uses quantum tunneling to an advantage to be able to calculate where is the highest probability of the least work necessary to come up with calculation results. So it's more like discrete versus analog computation, where gate-based quantum circuits use discretized on-off functions for gates and come up with measurable observations at the end of the circuit run. Whereas in an annealing circuit, it's more of an analogous computation using quantum tunneling to come up with the least probability or the highest probability of finding a certain outcome in a given dent in the state space. The net that I'm talking about is now a state vector space in which you're doing your calculations. It's a long answer, but that's the simplest summary I can give in distinguishing gate-based quantum computing versus annealing. And if you're interested in finding out more, I would say go to D-Wave, and they have a platform called Ocean, which is an SDK. Install it on your machine, and you can run the Ocean simulator to understand how annealing computation works. Okay, it uses a technique called Ising technique, which is something that I won't dive into, but it's specifically geared toward annealing computation. Long answer to a short question. Any more questions?
Despite reading out the next question, you have answered it, but still I'll read out the question. Do we need only quantum computers for QML, or we can use normal CPU or GPU system for QML programming?
So the answer is mixed. Remember the diagram I showed, which had two exponential curves and one linear curve? And it was showing, the time to calculate and the size of the problem. For simulations, you can use CPU, GPU systems using simulators, and you can install Qiskit locally, and you can install QSharp or QDK, Quantum Developer Kit from Microsoft, to conduct your experiments. You can install PennyLane, and do various kinds of simulations locally. The issue is your circuit depth in terms of number of qubits available, as well as number of gates you can apply, is bound by the amount of CPUs you have, the cores you have on your laptop or classical computer. It's also limited by the amount of memory you have. Okay, so it becomes very quickly IO bound based on how large or small of a machine you're putting these simulators on. You can use simulators to test and validate quantum circuits before you scale them to larger circuits that can use larger cloud-based virtualized machines that are much more capacious in doing larger simulations. But even there, getting to 1620 qubits is the max today, with the largest NVIDIA GPU-based compute clusters. The reason is simple. The input matrices become enormous when you start surpassing 16 by 16 matrix size, okay? Classical computers just cannot keep up with larger matrix inputs. They will not be able to solve for millions of years if you keep the CPU-GPU combination running on crunching a quantum circuit on a simulator. And QPUs are not scalable enough to go beyond 32 qubits today, and they're error-prone, as I mentioned before. So we are in a quandary balancing out how large of a problem can we validate on classical simulators using quantum circuits versus using real device QPUs where you have noise that prevents meaningful outputs for large numbers of qubits. But you can install simulators locally and play with them. Okay, next question is how to start research in quantum computing in academic institutions. What are the minimum resources required, and can you recommend some simulators? Yeah, that's a really good question. You know, you can play with all the simulators that are mentioned in the references, Qiskit, QSharp, PennyLane, and there may be other simulators that you can download, like the Ocean SDK. Rigetti has a Forest SDK. They called it Forest for some reason, but it's Docker based, and you can drop a Docker container on your classical servers if they're cloud based, or on your classical personal machines or workstations, and you can look at the SDK documentation, which shows exactly how to build quantum circuits for these specific frameworks and experiment with those. So I would advise that you can start out doing research using these SDKs and learning from the documents and going through the tutorials. There are some baseline installations that you have to do, which, if you reach out to me, in the last slide, my email address is there, rajiv@pivotport.com, or you can reach out to Dr. Sridevi. We are happy to help you with guidance on how to set up your local dev environment to play with simulators. And then, of course, you can start to look at various sources on the web for research papers that are being published. There's a very vast ecosystem of research papers that you can study and learn from. You can also go to YouTube, which has excellent QML materials. There's one series that I actually forgot to put the reference link for on YouTube, but it's a complete series on how to do QML. And I'll share the link offline. And Dr. Sridevi, if you can share it with the audience later on, I'll modify the deck with the reference to that YouTube series so you can learn QML using that course. It's free and you can experiment with it.
Yes, sir. Sure, sir.
Okay. Why are there bottlenecks? Okay. Why are there bottlenecks that do not accelerate training time when training quantum circuits with something like PennyLane, PyTorch, TFGPU libraries? Again, the bottlenecks are simply because CPUs, GPUs become very quickly bounded by the size of the input matrix. So the encoding that you have to do for submitting input data to a quantum circuit requires linear algebra-based manipulation of the input signals to create matrices. And the matrix object, the quantum object that is submitted to quantum circuits for calculation, becomes very large as soon as you have a large number of columns and rows in the input matrix. So depending on the number of cores available on your classical machine where you're running a simulator, and depending on the amount of RAM available, you may become range bound in terms of how large of an input matrix can your quantum object be before the quantum circuit either just outright fails to compute or takes an inordinate amount of time to complete its execution. Case in point, I'll give you an example. When we started doing quantum Fourier transform-based cardiac anomaly detection, we used the same MIT data set that Dr. Sridevi used for taking the input signals and encoding them into quantum objects using matrices, okay? And we use Qiskit using Python programming to do all this. When we ran the simulation, just at 8 qubits on our personal laptops, it was taking 3 days to compute a simple quantum circuit execution of a 7-minute input waveform for cardiac anomalies, okay? When we took the same circuit and put it on Azure VMs with larger memory and larger number of cores, it took a day. When we took the same circuit and submitted it to IonQ provider QPU, It took 3 minutes. This is the difference that you experience moving from simulation to QPUs. Okay, so the bottlenecks are driven by the size of the input matrix. That's my summary answer to that question. Last one, are there any certifications that we can do in quantum? Yes. If you go to edX, edX.com, or the edX application, and look for quantum coursework, you'll find a whole lot of quantum courses being offered by various academic institutions. There are some by Purdue. I finished a MicroMasters in quantum technology on edX from Purdue, and it is a fantastic 10-month-long course. It covers quantum fundamentals, quantum algorithms and software, quantum hardware, quantum detectors, quantum sensing, error and noise mitigation, and quantum networks. It's an extremely hard course to take on. So before you commit to a course like that, please make sure you're A, available for it for the 10-month period, and B, you have the requisite linear programming background in terms of being able to do the calculations necessary for these courses, because the prerequisite is quantum mechanics, and you have to have studied linear algebra. Okay, and then you can engage on these types of courses. Of course, on YouTube, you can also go study individual courses, but those don't give you a certificate that gives you an academic credential. One other thing, PivotPort is thinking of starting to offer apprenticeships where you learn by hands-on execution of quantum applications that we develop and we then deploy on the PivotPort quantum cloud environment that we've set up. So this is something that we have not yet formed fully, but if you go to the PivotPort website, under the quantum services workforce development page, you should be able to see a couple of examples, or on the PivotPort YouTube channel, which is mentioned in this deck, you'll see a couple of videos of quantum interns that did some summer projects over 2 months last year. One was on automotive input analysis for anomaly detection in automotive engine performance. Another was financial portfolio forecasting using VQE and SVMs. So, these are things that you can consider, and please reach out to me or Dr. Sridevi, and we can help you engage on certifications. Okay, how much time do we have remaining? I think we have 5 more minutes. So I'll take the last one, and then I'll hand it back to the host, Dr. Sridevi. Why doesn't QML consistently improve detection, classification, accuracy across all data sets? And why does it sometimes degrade performance compared to classical models? Again, QML is subject to QPU error and noise mitigation. And also, depending on the QPU platform that you chose, you may have different types of noise that creep in at different parts of your quantum circuit lifecycle of execution. So, again, QML has its own dependencies on how well you're conversant with tuning it for bias and the other factors that I mentioned earlier, variance and bias, as well as overfitting, underfitting. These are still more art than science. You have to empirically experiment iteratively to get to a converged solution. And, it's not like you execute it once and you have an answer. The next time you execute it, the same QPU might perform differently because it's probabilistic outcomes that you get. So this is something where you need to have multiple iterations before you can say, okay, my average answer is X, Y, or Z. Okay? All right. I'm going to thank the audience, and I'm going to conclude my presentation. And back to you, Dr. Sridevi. Thank you very much.
Thank you very much, sir, for this wonderful session. And from the participant side, also there were overwhelming response in terms of asking multiple questions. So thank you very much for enriching our on behalf of commemorating this World Quantum Day 2025 celebration. So it's a privilege moment for us. So now, to formally conclude today's event, I would like to deliver the vote of thanks. So, good evening, everyone. As we come to close of this insightful session on quantum machine learning organized in honor of World Quantum Day 2025, it is my privilege to deliver the vote of thanks. First and foremost, I extend my heartfelt gratitude to our esteemed speaker, Mr. Raju Mistry, for his enlightening lecture, answering the question and question session.
Thank you very much.
More patiently with detailed answers. So your talk beautifully bridged the realms of quantum physics and machine learning, offering us a glimpse into the immense potential of this interdisciplinary field. Your clarity, depth, and enthusiasm have truly inspired us. I would like to sincerely thank our Dean and Associate Dean of Research and Development for their support and for setting the tone of this evening with a thoughtful introduction on the significance of World Quantum Day. A special thanks to all the faculty members, students, researchers, and participants who joined us this evening. Your presence and engagement made this event more meaningful. So let us carry forward the spirit of innovation and curiosity that the session has ignited. May this be the beginning of deeper explorations into this quantum world. Thank you and have a wonderful evening. So once again, I would like to thank Mr. Raju Mistry for sharing your experience, I would say, in this evolving field. So having such a experienced person to give a wonderful session, so it's a privilege for us once again, sir. Thank you very much. Thanks a lot.
Thank you.
Thank
Thank
you.
you very much, sir. Yes, thank you very much.
You're welcome. Take care. Thank you. Bye.
Thank you, sir.
Bye, sir.
Bye, sir. So thank you, participants, for joining the session. So I'm stopping the recording.